Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video. All math-based, of course. And as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside. Let's go ahead and look at section 3.4 of the Big Ideas Math Integrated Math 2 textbook on graphing in vertex form. Now, I caught a sneak peek as I was trying to figure out what problem set we were going to have, and I think it's close to 80 problems, so come to my surprise. Looks like they're also doing some things regarding even and odd functions, and I think that's actually what I'm looking at, what we're going to begin with here. It doesn't really have to do with vertex form, it's just where they fit quadratics, so that's fine. Vertex form is kind of my favorite. It might be your favorite too when it comes to graphing, because it's the least amount of work. It's like the slope-intercept form version of graphing quadratics. And in fact, if you were with me for section 1.1 on graphing absolute value functions, it should pretty much be the same. You have an HK for vertex, you'll see it, but you have an HK for vertex, and as long as you know how to use the A value for quadratics, as we've been doing from section 3.1 to 3.3, including the quiz review, or the quiz or whatever you call it, then you should be good. So plot the vertex and go, go, go. I guess that's why they have some other things to talk about. That's why they have numbers up to like 80 problems or something like that. But let's take a look at the lecture first and see what kinds of problems we have to deal with here. We are going to identify even and odd functions. I guess that's the beginning part. Graph quadratic functions of the form here, a times x minus h quantity squared. There's no plus k yet, and then they throw in the plus k, so I guess there's that. And model real-life problems using that. This is also known as vertex form, and I hope they're going to call it that. It looks like it. They're going to call this thing vertex form right here. So we'll dive into it when it comes along. Even and odd functions. Let's talk about these. A function is even when, now this is going to look kind of strange. I'll get as many description things as I can. When f of negative x equals f of x for each x in the domain of f. Okay, what they're saying is if I substitute some value for x, or if I substitute the opposite value of x, I get the same y value out. So on a graph, if I plug in this value for x and I get this y value out, and I plug in this opposite value of x and I should get the same y value out. That's what even functions do, that they have this kind of symmetry. And that's what they're going to say next. The graph of an even function is symmetric about the y-axis. Here's my y-axis right here. Pretend like that green line's your axis of symmetry. These 2 points are the same distance across. Parabolas can be even functions as long as they're symmetric across the y-axis. But parabolas are an example of it, maybe why they're bringing it up. But they also bring up odd functions, so not maybe necessarily. We'll see. A function is odd when if you substitute the opposite x value, you get the opposite y value for each x in the domain of f. It's an odd graph of an odd function is symmetric about the origin. So what that would look like is in a case of I plug in this x, I get this y out. Now I plug in the opposite x, and I get the opposite y out. So it goes down here. Now, these are single points. These are single points. We're going to talk about entire curves or, polynomials, which represent these things and whatever, and which ones are even or odd. Now, they say them with these variables here, and we are literally going to use these variables when it comes to examples. You'll see them down below. If a function is not even or not odd, then it is neither. A lot of functions are neither. They have to be actually symmetric across one of those things. Symmetric about the origin means that we can rotate this thing 180 degrees and we get back to where we were. We'll see some that are visuals, I'm sure. Oh, they say that, 180 degree rotation. We'll see some of these visually, I'm sure, with actual graphs, and I can point to them. There are some little tips and tricks with polynomials to determine whether they're even or odd. I could tell you right now, this is odd, this is even, and this is neither. I just know that, but we're going to go and take a look and see what they do. What we do work-wise. F of x equals 2x. Here's the original. Remember, f of x means y. Let's find out if this is an odd function, even function, or neither. Let's substitute negative x into here. And they don't mean plug in a number, because you can have what are called false positives, meaning it just so happened that my opposite value happened to hit the same height, but maybe I was lucky for that point or a couple points. Let's find it for all points. F of negative x means we substitute negative x in for x. And keep that in mind, guys. Whatever is here for your input will take place of your input. Will take place of x. X turns into negative x. And all I want you to do is simplify what's there. What happens is it turns into negative 2x. And you know what negative 2x is? It's the opposite of 2x. You know what 2x was? F of x. So this is the opposite of f of x. Because f of negative x equals negative f of x, the function is odd. So what they're doing is they're saying when you substitute negative x, what kind of result comes out? What result comes out is you get the opposite values for y. Remember, this is a way of saying here are the y values that come out when I plug in negative x. And what are they? They're the opposite of the y values that I get out when I plug in x. That makes it an odd function. Makes it an odd function. And, we'll look at visuals of linear functions, of all these functions later, hopefully, or something like that. So that's an odd function. So it's kind of a proof with that. Part B, let's substitute negative x into here. Use parentheses when you do substitution, especially something like this. We square negative x, and it becomes positive x squared, right? So what happens, think of negative x as negative 1 times x. Negative 1 times x squared is negative 1 squared times x squared. Negative 1 squared is 1 times x squared is x squared, right? So that's what negative x squared gives you. It gives you positive x squared. The goal, the idea there is no matter what I substitute for x, positive or negative, when I square it, it'll turn into the equivalent of what would happen with the original value, whether it was positive or negative. And keep in mind, our x values don't necessarily have to start positive. They're just changing sign. They're saying what happens when you change sign. So there's something else to keep in mind as well. Anyway, minus 2, there's no x in that, so that stays the same. So you get x squared minus 2 back out. And guess what? The original was x squared minus 2. So this is the same as g of x. So when I substitute negative x into here, I get the same y value out as I would, right? Because these are identical. So if they're identical, you get an even function. If they are exact opposites, you get an odd function. This is an even function because plugging in negative x gets me the same y as if I plugged in a positive x. Now, this third one's kind of a mix. You plug in negative x into here. When you square it, it becomes the same as what 2x squared would be. Boom. And you add negative x, that becomes minus x. Now, this is different. You have 2x squared plus x minus 2 and 2x squared minus x minus 2. Only one term changed, not all of them. It's not the exact opposite, and it's definitely not identical. Really close. But it's neither even nor odd. It's not exactly the opposite of h of x or the exact same as h of x. So this is a case of neither even nor odd. Anyway, I explained it very long there. I'm not going to explain it as long in my problem set unless there are new developments I need to bring up. Okay, so that's your bigger explanation. There were no visuals. No visuals. When we hit visuals, maybe I'll slow it down, unless they let us do some more. Okay, not right now. So we are first going to be graphing f of x equals a times x minus h quantity squared. Now keep in mind that we did do vertex form for absolute value functions. So we did have a plus k at the time. We're going to bring it back. But the x minus h quantity squared, if the plus k is plus 0, that means there's no vertical translation here. All we're looking at to begin with, because we did solely vertical translations at the time with ax squared plus c, well, now we're going to look at a times x minus h squared, which means just horizontal translations. And I'm not going to get deep into the talk. Once again, it's something that I've done in the past. But the x minus h squared means you're trying to seek what values of h we have. When h is greater than 0, the graph of this thing is going to translate to the right. So when h is a positive number, if h is positive 4, it'll say x minus 4. And we're going to go 4 to the right. If h is negative, less than 0, then we're going to be translating units to the left. If h is negative 4, that's x minus negative 4. That's x plus 4. We're going to go 4 units to the left. It is the opposite. There are reasons for it. It has to do with what we're substituting for x to give us 0. But this is part of where vertex form exists. Straight translations, left, right, horizontal, that's what we're going to have. So it looks like we're going to be doing some sort of, besides graphing them, we're also going to be describing transformations, I'm sure. Yeah, graph g of x equals 1/2 times x minus 4 quantity squared. Compare the graph to the graph of f of x equals x squared. So let's see if they graph it first. So we start by plotting the vertex. Because h is 4, x minus 4, h is 4, we're going to plot it at 4, 0. How do we know 0? Because it doesn't translate up or down. There's no k yet. So we plotted at 4, 0. They say find and plot 2 more points. If you follow along with me, I'm going to go over 1, up half of 1, over 2, up half of 4, things like that. And I'm going to plot my own points. But here's the blue graph. It is vertically compressed by a factor of 1/2, and it's translated 4 units to the right. So let's see their description. They compare everything. They say both graphs open up. That's great. They say it's wider. I'm only going to state transformations when I do. I'm going to talk about the vertical compression by a factor of 1/2, translating 4 units to the right. So they do mention, they mention axis of symmetry and stuff as well. Translated 4 units to the right, and vertical shrink by a factor of 1/2. That's going to be my goal. Okay. Now we do it with the plus k. So the plus k is including a vertical translation as well. So you know me, I'm going to start from the vertex, and then I'm going to apply the a value. So they mentioned the hk. how far over, how far up, plot every point in relation to the vertex. Your vertex is at HK. K does not have a flipped sign when it says plus K. If it said plus 7, K is 7. Whereas if it said plus 7 for H would be negative 7, right? So it's that flip thing. The axis of symmetry is at x equals h. It's the vertical line there for the vertex value, right? And then the k value represents a minimum or a maximum. I don't know if they mentioned that, but okay. Graph -2, g of x equals -2 times x plus 2 quantity squared plus 3. We're going to begin with the, well, they graph the axis of symmetry first. I kind of graph it after I draw the vertex, but they start with h as -2. Remember what you plug in for x to make this 0. When you plug in -2 for x, this all turns into 0, plus 3 is 3, and it ends up being a maximum in this case because it's negative. It goes upside down. But your vertex is at -2, 3. We start with plotting that right there. And then, like I said, they're going to use tables. They're going to reflect across points and all that kind of stuff. I'm going to just plot points. Over 1 down 2, over 2 down 8. We're going down because it's negative. We double 1, we double 4. 1 squared and 2 squared. We plot as many points as we can fit. I will reflect across the axis of symmetry. Note this y-intercept of -5. This is no longer your y-intercept because that's not what remains when x equals 0. You want to find out your y-intercept, you have to plug in 0 for x and compute, or expand it into standard form and see that you're going to get a plus 5 in the end when things combine properly. So there's a y-intercept, but it's not featured in vertex form. Vertex form gives you the vertex, and of course the stretch factor. They ask you to compare these things. I'm going to say we reflect over the x-axis. We vertically stretch by a factor of 2. We translate 2 units left, 2 units left and 3 units up. So they say those things: vertical stretch by a factor of 2, reflection in the x-axis, translate 2 units left and 3 units up. Okay, this new kind of example is really important that I'm seeing here. They say graph f of x equals g of x plus 5. Excuse me. So g is the original. Okay, so g is the guy in blue. No, g is the guy in black. G is the guy in black right here. Some graph, and they say do this stuff to it. F of x is going to be our new graph where we're going to be doing this to it. Now this thing's on the inside. This is where, they didn't ask us, let's see, I'm trying to find it. They didn't ask us to actually do the thing inside, and I probably will for some problems, but this x plus 5 is the same thing that would happen with this x plus 2. We go 2 to the left on this guy, so this would be going 5 to the left. Things are going to be 5 farther left than they were before, because we have to make values that are 5 smaller to compensate for the fact we're about to add 5 to them. If you don't understand that in full, that's fine. If you do, then I hope you pick something up off that. But basically, when we graph this thing, we're going to translate it 5 units left for the same reason we translated that 2 units left. So that's already 2 units left plus 3. Now another 5 units left will give us our new graph. We're going to see other ones like that. Like I said, it's so this one right here, this is outside of the function, not inside of it. This is a vertical translation. So we're going to have to get really used to that whole x, h, k stuff. Like literally, I could say that I have some g graph that is a translation of f such that it multiplies by some a. We have some x minus h and plus k. We could use all these numbers here, and a could be negative and all this kind of stuff. This would still be, it doesn't have to be a quadratic. It doesn't have to be an absolute value function. It could be whatever function you want it to be. Whatever the function you want it to be, right? A would be a vertical stretch, compression, or reflection. H would be a horizontal translation. K would be a vertical translation. And whatever these things are, when it's inside the function, we go left, right. When it's here, you go up, down. And here you stretch, shrink, or reflect. So we're going to see some of those, I'm sure. All right, some real-life problems. Maybe this is our last page before we start our problem set, or at least our vocab and concept check. Water fountains. Water fountains are usually designed to give a specific visual effect. For example, the water fountain shown consists of streams of water that are shaped like parabolas. Notice how the streams are designed to land on the underwater spotlights. Write and graph a quadratic function that models the path of a stream of water with a maximum height of 5 feet, represented by a vertex of 3, 5, landing on a spotlight 6 feet from the water jet, represented by 6, 0. So if I'm to, so that, they say understand the problem. So if I'm to understand the problem here, I'm guessing they're saying that like from one point to another, this is kind of like the axes, and then you make a parabola that does its parabola thing. So I'm going to kind of stream that like that. It goes up, it goes back down there. We have a 0.35 right here, and then later it hits a light thing over here that's 6, 0. Hopefully you can kind of see that. So that's the idea, and they're saying write an equation. So let's write the equation, but let's do it in vertex form, because we have the vertex. That's good. What we need to do is determine this a value. There are a lot of different ways to do it. The textbook way, no pun intended, the textbook way to do it is by a substitution of values. If we can substitute 6 for x and get 0 out for y with this vertex, what a would have we had to have had for that? That's what we're going to try and figure out. So understand the problem. You know the vertex and another point on the graph that represents the parabolic path. Boom, boom. You are asked to write and graph a quadratic equation, that function that models this path. You use the given points in the vertex to write a quadratic function, then graph the function. So 3, 5 is your h, k. They are your vertex values. 6, 0 is just some xy value among all the infinite xy values that exist on this graph. But 6, 0 is one of them that we know for sure. So we can plug 6 in for x and 0 for y with an equation that we already have 3 and 5 here based on just how vertex form looks for a quadratic. So there's the beginning. F of x equals, or y equals, a times x minus 3 quantity squared plus 5. Let's substitute 6 for x and 0 for y because it represents one of the infinite numbers of solutions that we have here. And this one will give us a specific a value that represents this scenario. 6 minus 3 squared is 9. And there's still a plus 5 here. So we have 9a plus 5. I subtract 5 from both sides and divide both sides by 9, or the book does, and you get a as negative 5 ninths. So negative 5 ninths is the vertical stretch factor, or compression factor in this case, and reflection component that gives you this equation here. F of x equals negative 5 ninths times x minus 3 quantity squared plus 5. That models the path. There's more that I can say with those kinds of problems. You're going to see me do them, but the basic construct is how I generally do these graphs to begin with. How far did I go over from 3 to 6? 3. How far did I go down from 5 to 0? I went down 5. Normally, I'd go down 9, right? Normally, I'd go up 9. If I would normally go up 9 and I'm multiplying it by some a to get negative 5, what is that a? Negative 5 ninths. It goes a lot faster, but you get the exact same answer into the exact same portion. I guess we don't write the portion where we subtracted 5, but to the exact same portion here by saying, I would have gone up 9 because that's 3 squared, but now I'm multiplying by some stretch factor to get that. What is that value that I get? Quick algebraic setup. Some of them you can do even mentally without writing that. Okay, graph the axis. Oh, so now they want you to actually graph this thing. So, okay, there's a graph. We start at 3, 5, and I don't know, they plotted some points there. We can come up with 5 ninths of whatever. You know, I want to come up with 5 ninths. Oh, wait, that would be the intercepts, but I'd come with 5 ninths of 9. But that would be the x-intercepts. What else did they ask for? That's it. Write and graph thing. So they do. Okay. Okay, guys. That is the lecture portion of this. Let me pause for a sec. I have a couple sniffles. Okay, the sniffles may come back. Who knows? But let's go ahead and take a look at the vocab and core concept checks. We haven't had 4 questions in a while. They've normally been 2. But we got a lot of problems to do after this, I tell you. Compare the graph of an even function with the graph of an odd function. The graph, so this goes back to what we first began talking about. An even function is symmetric across the y-axis, and we still haven't seen a graph of them. I mean, you can imagine them, but the graph of an even function is symmetric across the y-axis, like a parabola can be, and the graph of an odd function is symmetric across the origin. So again, I'm sure we're going to see some, and if not, we're just going to have to deal with what they give us. All right, write a quadratic function whose graph has a vertex of 1, 2. So open-ended kind of thing. 1 would be your h, 2 would be your k in this scenario, and your equation is the y equals a times x minus h quantity squared plus k. Our basic thing is we need to come up with our own a value, even if it's 1. I'm going to come up with one of, say, negative 4. Y equals negative 4. Times x minus h, that's x minus 1, quantity squared, plus k is plus 2. There's an example of an answer right there. Plug in whatever you want for a, or completely leave a out, meaning it would be 1. But in that case, that's 1. Describe the transformation from the graph of f of x equals ax squared to the graph of g of x equals a times x minus h quantity squared plus k. This is where you start throwing in those components. So the transformation here is all about your h and k, and we don't need to know what they are. We're just going to say h units and k units and things like that. So they're the same in every respect except translations. We would translate f h units to the, well, hold on. We'll translate f, hold on. I just don't want f and h to be right next to each other. We'll translate f, there we go. H units, I was trying to find another way to say the sentence. Horizontally, left if h is negative, and right if h is positive. And 0, we don't move it left to right at all if h is 0. We translate h units horizontally and k units vertically. We would go up if k is greater than 0, and down if k is less than 0. And that's kind of it. The axis of symmetry is at x equals h instead of x equals 0. The minimum or maximum is at k instead of 0. Those kinds of things. But that comes with the transformation itself. They said describe the transformation, so I think that's it. All right, which function does not belong with the other three? Explain your reasoning. So I'm going to call this one A, and let's compare these things here. F of x equals 8 times x plus 4 quantity squared. This is a vertex form equation. This one says f of x equals x minus 2 quantity squared plus 4. They aren't the same equation, but they're both vertex form. What are they asking us here? Let me look at all three and see what they're talking about. Which function does not belong with the other? They might be talking about this one being different because this one has no translations. X plus 0 is the same thing as x. That would be f of x equals 2x squared, whereas all these have at least a horizontal translation, if not also vertical translation. That's one thing I'm looking at. There's more than one answer to this thing. It could be this. It could be this if this is no translations, but you know what this one doesn't have? This one doesn't have a vertical stretch or compression to them. These ones all vertical stretches. 8, 2, and 3 are all vertical stretches. But they're all in vertex form otherwise. That's going to be my thing. So my reasoning is because no translations. In an alternate reality, we could say A, and B. If you want to say no vertical stretch compared to the other ones. So I don't know. I don't know which one they're talking about. I'm going to assume they're talking about the translations because it's all about vertex form. So I'm really living on that first one. Okay, we're about to hit these problems here. Before we begin, I just want to make sure to remind you that you might want to download some graph paper down below. I'm going to use the tall version if I need to, based on whatever graphs they have us do. There are going to be timestamps for the problem set down below as well. I need to pop up one more thing too. But anyway, I'm going to, timestamps down below, find the playlist for IM2 stuff down below if you're having trouble with the graphing stuff. It says 79 problems, guys, so 5 to 79. So I'm going to do a lot. And I want to do it in as little time as possible. That means if you see me graph before, this is going to make a lot of sense given the A value stuff, especially if you've done vertex form stuff with me before, whether or not you skip the lecture. But I'm going to go ahead and get started with you guys here. Okay, so let's move and look at numbers 5 through 12. Determine whether the function is even, odd, or neither. Now, once again, as long as it's a polynomial, I could tell you right off the bat which ones they would be. However, that's not really the thing we want to talk about here. I could talk about it at the very end. Maybe you'll make sense of it then when we do it. So here's the original function. What I'm going to do is substitute negative x in for x. It's going to take its place. So we'll get 4 times negative x plus 3. Now we're going to simplify that. 4 times negative x is negative 4x, and we get negative 4x plus 3. Now, there's only two questions that we ask ourselves. Well, there are two things that we check for. Is this the exact same as this function? Are these the exact same? No. Is it the exact opposite? No. One of the signs changed, the other one did not. Now, one thing you're going to see me do a lot is like this factoring thing. Not in this case because it's obvious that it's not, or at least obvious enough. But if I factored out a negative, what's inside after is 4x minus 3. My real goal or my check to see is if factoring out a negative 1 gives me the exact same thing that was here. And it doesn't because 3's sign changes. So this is not the opposite of f of x. It's not the opposite of f of x. It's not the same. This is a neither case. Neither even nor odd. Neither. And that's what we're looking at there. Number 6. G of x equals 3x squared. Now again, if you saw the lecture portion, this will help out as far as seeing what I'm doing and why. G of x equals 3x squared. Now g of negative x would be 3 times negative x quantity squared. And when you square a negative x, it becomes a positive x again, 3x squared. 3x squared is the same thing as you saw above. That means g of negative x, is the same thing as g of x. That's that take-home message. If these are the same, I get the same y from different x's, you have what is known as an even function. This is an even function because you get the exact same thing out as you had before. Number 7. Not a polynomial, it's an exponential function. H of x equals 5 to the x power plus 2. Now h of negative x would be 5 to the negative x power plus 2. And if I were to simplify that, 5 to the negative x is 1 over 5 to the x power plus 2. That is not identical with this in any such way. The 2 may be the same, but this part's not. Whether it turned negative, whether it reciprocated like that, this is once again in neither case. It is neither the same or the exact opposite as h of x is the original. Number 8. M of x equals 2x squared minus 7x. Let's check out m of negative x. That's going to be 2 times negative x quantity squared minus 7 times negative x. So negative x squared is x squared times 2 is 2x squared. Negative 7 times negative x is positive 7x. 2x squared stayed the same. The 7x changed a sign. This is in neither case once again. It is definitely not even because they're not the same, and it's not odd because not all signs in the polynomial are opposite of each other. If I factor out a negative, I don't get the same thing. Now it's interesting because I was gonna make mention about saying that, hey guys, you know all the even odd functions that we're seeing here? Don't expect that all the time. They're not technically all that, but because they're testing for even or odd, you should expect a lot of even and odds. So far we've only had a single even, no odds yet. We're gonna see where we go from here. Number 9. P of x equals negative x squared plus 8. Now, when I do p of negative x, keep in mind, this negative is outside of the x and outside of the x squared, in fact. This is negative x that's being squared. We square negative x first. We don't do negative times negative because PEMDAS. We're going to go ahead and square the negative x first, which is positive x squared. But then we take the opposite of it, negative x squared there and plus 8 there. These are identical. These are identical. So p, not g, p of negative x is the same thing as the original p of x. That makes this, once again, an even function when they are identical to each other. Remember, this is for any x, right? I can plug in 3 into here and negative 3 and see that I get the same value out. 10 and negative 10, or x and negative x, and see what happens, just like I did. Number 10. F of x equals negative 1/2 x. F of negative x is negative 1/2 times negative x. And multiply a negative by a negative, you get a positive. You get 1/2 times x, which is the exact opposite, right? This is the exact opposite of negative 1/2 x. And I know that that looks weird to show a negative with a negative there, but I'm showing that this is the exact opposite of this. Excuse me, of f of x. This is the opposite of f of x. And that's what f of negative x was. When I plug in a negative x, I get a negative y result out compared to the original x that I would have plugged in here. That is what an odd function does. This is an odd function for number 10. Number 11, we have n of x equals 2x squared minus 7x plus 3. So n of negative x equals 2 times negative x squared minus 7 times negative x plus 3. Negative x quantity squared is x squared times 2 is 2x squared. This is a plus 7x here, and plus 3, that's going to do that. So almost identical, except instead of a minus 7x, you have a plus 7x. Nothing else changed. This is a neither case. It's not exact opposite. It's not exactly the same. Neither case, neither even nor odd. And one more as I'm kind of running out of room down here at the bottom of the barrel, number 12. R of x equals negative 6x squared plus 5. R of x equals negative 6x squared plus 5. Okay, what's R of negative x? That is negative 6 times negative x squared plus 5, or negative 6 times x squared plus 5. They're identical. They are identical. This makes an even function. Let me write that. Equals R of x. So they are the same when you plug in the negative or positive there. Okay, before I move on to the next ones, I wanted to make mention of something that you might see a connection with on all of these problems here. In polynomials, meaning every problem that wasn't number 7, if we know what polynomials are from chapter 2, in polynomials, if you only have even degree terms, that's degrees 0, 2, 4, 6, 8, 10, etc. If you only have even degree terms, you will have an even function. Period, point blank, end of story. In polynomials, if you have only odd terms, 1, 3, 5, 7, 9, you will have an odd function. In polynomials, if you have a mix of even and odd degree terms, 1, 2, 3, 4, 5, etc., it will be a neither case. Consider the first one. This is how I knew so fast. This is degree 1, this is degree 0. That's an odd and an even. Automatically with that mix, it'll be a neither. This is degree 2, that will absolutely be an even. This was not a polynomial, it's worth testing that one. This is degree 2 and 1, that'll be a neither. This is degree 2 and 0, both even. Degree will be even here. This is degree 1, the only degree, that'll be odd. This is degrees 2, 1, and 0, there's a mix, that'll be neither. And degrees 2 and 0, that'll make it even. Now, why is that the case? Because the degree has to do with the exponent of your variable. Whenever you raise a negative number to an odd power, it stays negative, which means for you, the sign changes. If all of the signs changed, then it's the exact opposite of it. If it's an even function, if it's all even degrees in your thing, and you raise a negative number to an even power, or in degree 0, like a constant, you don't raise it at all. Not raise it. If you take a negative, or you don't substitute anything with the degree 0 at all, none of the signs will change, because squaring a positive stays positive, squaring a negative turns positive. So they would stay the exact same, and that's kind of why that happens. So this way you can sneak peek it, even though you probably have to show your work. Or they're not all polynomials. Remember, that's only for polynomials that I'm talking about that. Not square roots and rationals and exponential and things like that. Okay, number 13. 13 through 18. Determine whether the function represented by the graph is even, odd, or neither. Okay, I'm not going to copy down the graph. I'm going to utilize the graph to talk about these, though. Here's the visual where we can actually talk about evens and odds and stuff. This first graph here, if you notice, when I have an x, I get some y value. When I plug in 1, I get 1. When I plug in negative 1, I also get 1. You can see the symmetry across the y-axis right here. Same distance away, you have the same height. That's what even functions do. They're not all parabolas. They're not all parabolas. You can have different kinds, but parabolas can have that, especially if the vertex is at the origin. This is an example of an even function. Opposite x's get you the same y. So I'm literally just going to write the answers here. Even. Now, my actual goal for these is not to show when something is even or odd, but to show when it's a neither. But I do want to support the evens and odds here if they show up. Number 14. Number 14, if I plug in some x and I get some y, like I plug in, and I can use actual example numbers with this, but I plug in 2 and I get negative 1, and then I plug in negative 2 and I get negative 3. Opposite x's did not give me either the exact same y nor opposite y's. This was not symmetric across the y-axis. This was not symmetric across the origin. This is a neither case. Number 14 is a neither case. Number 15. I have what looks like an exponential function. It crosses through the origin, but does that make it symmetric across the origin? It could. It actually almost has the liking of it. So there's 0, 0 where it hits there. It doesn't have to, but it can't cross anywhere else on the y-axis and be symmetric. I plug in negative 1 and I get 1. I plug in positive 1 and I don't get negative 1. I get maybe negative 1/2 or something along the lines there. These are not the same, these are not exact opposites of each other there, right? I plug in negative 2 and I get 3. When I plug in positive 2, I don't get negative 3. I'm not getting the opposite, clearly not getting the same. This is not symmetric across the origin here. Negative 2, 3, and positive 2, that number right there. Not exactly opposites. This is once again a neither case for number 15. All right, I'm going to speed up now. Number 16. If you can, sometimes you can take a look and just tell. You just know about symmetry, like when you see a face or something. That looks like the makings of the chin of a face there, number 16. That is going to be an even function, symmetric across the y-axis. You'll have to know it by name, but you know what's helpful is knowing that quadratics, or parabolas, excuse me, are quadratic. Quadratic is a second degree, and if you think second degree, you think even numbers. Number 17, this might actually have odd degree behavior. I plug in -3, 3, I get -3. I plug in -3, I get +3. I get the exact opposite y's for the same x, and that apply, or for opposite x's, and that applies for all points on this thing. This is what an odd function does. And then number 18, it's a parabola, all right, but it's not symmetric across the y-axis. I get a point here that's 2. I get 1. I get 1 again when I plug in something right there in between, maybe 1/2. But when I plug in -2, I get something way down here. I have no idea what it is. This is a neither case as well. This is just, it's a nothing burger. Number 18 is a nothing burger. I was going to say nothing, neither. Okay. All right, and that is the first set. So I guess those went kind of fast, especially if we have to talk about them more. I will go very fast with them, but it's not as slow as graphing. Okay, in 19 to 22, find the vertex and the axis of symmetry of the graph of the function. They don't ask me to graph, and I'm not expecting to necessarily. I can do little rough sketches, but that would be it. F of x equals 3 times x plus 1 quantity squared. All these look like they just have the x minus h quantity squared. They don't have the plus k. That means this is a plus 0, though, which would make the k value be 0. So your vertex is going to be at -1, 0. We're always going to have the 0, and the h is opposite of what value you see there. So -1, 0 for the vertex. The axis of symmetry will be at x equals -1. It is the line that goes through the vertex. It's vertical, and that's what those are going to look like. It's going to be pretty straightforward. It's going to be x equals h. Whatever h is, it's going to be there. And that's all they want. So I get to go probably faster now. Let's look at number 20, f of x. And by the way, the stretch factor had nothing to do with this because they don't ask whether it's a max or min. They don't ask about stretch, none of that. So we're all good. F of x equals 1/4. Oh, good enough. 1/4 times x minus 6 quantity squared. Your h is 6, positive 6. Your k is 0 once again. Your axis of symmetry is at x equals 6. Kind of some of the easier questions that you have here because the axis of symmetry is always the same as the x value for the vertex, and the y value of the vertex is always 0, and the a has nothing to do with it. Number 21, y equals -1/8 times x minus 4 quantity squared. Your vertex is at 4, 0, right? I plug 4 in for x, I get 0 out for y. That's the old end goal. So 4, 0. Your axis of symmetry is at x equals 4. I kind of feel like I'm supposed to be graphing this. Find the vertex of the graph of the function. They say find it, they don't say graph it. Number 22, y equals, yeah, because here they say graph, right? And the others they don't. I keep thinking, am I supposed to graph this? Y equals -5 times x plus 9 quantity squared. I think part of it is they're just testing to tell you that this isn't k. And you know what? I see a lot of my students call that k. They're like, oh, this is the same as -5. No, this is times -5. A multiplies with your function. So your vertex is at -9, 0, and your axis of symmetry is at x equals -9. So not much to say on those things. It's just, I think you're just practicing the form as well. Kind of what I said there, but that was only without k. We're still not going to include k on this next set here. 23 to 28, graph the function, compare it to the graph of f of x equals x squared. Okay, I don't have an intent on graphing literally the x squared graph itself. We're just going to talk about translations and everything we've done. So this is really combining everything we've done before while identifying vertexes, which we just did now, and we've done in section 1.1 quite often. So I hope that this will feel pretty good if you've been following along with me. The question is, are you still good at doing A? G of x equals 2 times x plus 3 quantity squared. So the vertex is at -3, 0. I'll graph the axis of symmetry with these ones as well, at least to begin with. -3, 0. 2, let's do the vertical stretch, the axis of symmetry right now. Can it be this thick and still be okay? That's pretty thick. Let's lay it on thin. Okay. 2, vertical stretch, it goes upward. Instead of 1, 1, 2, 4, 3, 9, 4, 16, we're going to go 1, 2. We're going to double that, reflect. Instead of 2, 4, we double the 4 and get 8. Reflect. You got to slow me down with the video slider. 3 over instead of 9 up, we double 9 and we get 18, which is off the graph a little bit. I'll put it on the line just to get it. Now we have to compare this to the graph of f of x equals x squared, the one before we translate and stretch. And that's what we're going to talk about. We're going to talk about its stretch and its translation. That's a pretty good looking curve. So we are going to vertically stretch by a factor of 2. And horizontally, we're going to translate 3 units left. There's your graph. Number 24. It tweets my back. I think from writing, because I have to like extend out. Number 24. We have p of x equals 3 times x minus 1 quantity squared. The vertex, oh, I have to graph this. The vertex is at 1, 0. So that now I'm actually just going to plot them. I'm just going to graph these now, guys. We go over 1 to triple our y values. Instead of 1, 1, it's 1, 3. Let's draw the axis of symmetry again. Hey, that's not it. By the way, these are not even functions if they're not symmetric across the y-axis, even though it has an axis. Over 2 up 12, that's 4 times 3. And that's all I can fit. Sorry. Okay, there we go. There we go. There we go. Compare it. I'm not going to do everything. I'm just going to not talk about the axis of symmetry. We vertically stretch by a factor of 3. Translate 1 unit right. All right, there's number 24. Number 25. R of x equals 1/4 times x plus 10 quantity squared. We're not even a third of the way done. We have a lot of word problems to look forward to. R of x, and I felt like the first questions were like fast, right? 1/4 times x plus 10 quantity squared. I can't really fit that well on this graph unless I change scales because the 10 goes all the way off the graph here. So for x plus 10, it would be over there. How about I make these 10s instead? Negative 10, like that. 1/4. I'll keep the 1/4 as it is, though, if that's cool. So I'm going to go ahead and plot this right there. Everything goes by 2s now right here. You have to be careful. These are still going to go by 1s. So 5, 10, and 15. I was going to say 20. But it does go upward. So x plus 10 quantity squared, this is your vertex at negative 10, 0. Over 1 up 4, or up a quarter of 1, I'm not going to fit. Let's go over 2, which is just one of these, and up a quarter of 4, like that. I don't know if it's going to be okay that I have this kind of appearance, but go with it. Over 4, right, 2, 4, up a quarter of 16, 4 squared, and a quarter of that is 4. So this is going to look like a normal graph just because the scales that I changed. Over 6, we go up a quarter of 36, which is 9. And over 8, we go up a quarter of 64, which is 16. So again, looking at my scales, you can see how this thing actually works out here. Now, I might put the original graph with this just to kind of compare, because otherwise this might look normal to you and say, this is not vertically stretched or compressed or whatever. This is just a normal one. Well, it's not, because I changed the scales. So if there's that one, x squared looks like, 1124. See, it's going to look like this now instead, because going over 2 is just one of these. 4 up 16, and it would end up, doing that. So compare the f of x equals x squared to r of x equals this guy. So f of x equals x squared, and this is r of x right here. Okay, so you can tell it's a vertical compression, or they say it's wider, things like that, but the 1/4 is a vertical compression. So vertically compress, fourth, and then stretch, translate 10 leftward. Okay, number 26. I think all of these other ones can stay in our window range enough that I don't have to change scales. That's not my plan to do that again. Number 26. N of x equals 1/3 times x minus 6 quantity squared. Okay. X minus 6 quantity squared, we're going to start there. Now, 1/3 is the vertical compression this time. So over 1 up 1/3 of 1. That's not a beautiful one. Over 2 up 4/3 of 1. That's, or excuse me, 1/3 of 4. So up 4/3. That's 1 and 1/3 like that. And over 3 up 1/3 of 9. 1/3 of 9 is 3. That's going to be nice. Now, I can't really fit anything going to the right anymore. I'll makeshift one more. But on the left, I can still fit them. Over 4 up 16/3. 16/3 is 5 and 1/3. So I can kind of still fit that one over here. Over 5 up 25/3. That's 8 and 1/3. Wait, what did I say about this one? It was what? This was over 3, 4. 16/3. 16/3, yeah, that's 5 and 1/3, right? Yeah. And then over, what did I say here? Over 5 up 25/3. So that's 8 and 1/3. And we won't really see the full reflection on this one here, but that's as best as we can do. 7 over 6 up 36/3. 36/3 is 12. And that's probably the last good point I'm going to find. 49/3 is 16 and 1/3. So that would look like that, because that's when I go over 7. So like I said, I'm not going to be able to fit the whole thing to show all the symmetry on this thing. But I plotted as many points as I could fit within my window range. And to me, that's kind of just as important. And I can't seem to go through the points. I'm sorry. Let's see if I can just go up just a smidge. I'll have to count it. Okay. That is number 26. Compared to F, we have the vertical compression and the translation that may be used in that direction. So we vertically compress by a factor of 1/3. And then we translate 6 units to the right. Just trying to make sure everything's good. Okay, that is number 26. Number 27, we have d of x equals 1/5 times x minus 5 quantity squared. Okay. Your vertex is at 5, 0. Once again, we still haven't touched k's yet. Maybe that comes next after the error analysis questions. So 5, 0, and 1/5. I got a 1/5 of 1. A 1/5 of 4, which is 4/5. Again, I'm saying these numbers based off of how far we go over. We go up that amount squared, but then times 1/5. 9/5. 9/5 is 1 and 4/5, like that. 16/5 is 3 and 1/5. And then the good one, 25/5 is 5, just like that. Just that day. Let's stretch it out to the next one. 10 squared is 100. 100/5 is 20, and that would have gone way 17, 18, 19, 20, probably way up there. So I'm just going to kind of mock or makeshift what that would look like if going through right there as a curve. You're taking a 1/5 of everything. Nothing was negative. Will anything be? Nope. All right, number 28. Q of x equals 6 times x plus 2 quantity squared. Oh, I'm sorry. Let me first say this before I keep going. There we go. Okay, number 28. Hopefully the last graph for a while. Q of x equals 6 times x plus 2 quantity squared. And once again, none of this has to do with even or odd functions, especially because these are even functions, or neither either nor odd. So they just threw that in there. Vertex is at negative 2, 0. Vertical stretch of 6. Wow. Over 1 up 6. Over 2 up 24. That is 4 times 6. I can't even fit that. So I'm just going to pretend like it's getting closer and closer. Do what I can drawing my curve. And there we go. There we have it. There is our graph. We vertically stretch by a factor of 6, and we translate 2 units to the left. Vertically. There we go. All right, those are my descriptions for those ones, numbers 23 to 28. Okay, let's go ahead and move forward to error analysis numbers 29 and 30. Number 29. Describe and correct the error in determining whether the function is even, odd, or neither. So everything looks good on the math. They substitute negative x here. They square negative x to get positive x. That's x squared plus 3. That's identical to f of x. F of negative x and f of x are the same thing. That would make an even function. They mentioned it was an odd function. So that is their one mistake on number 29. They stated it was an odd function when really it is an even. Now the mathy reason is just this, that f of negative x equals f of x, or rather you obtain the same height from opposite. Now this is all in the domain. So there's kind of a long-winded explanation of what that thing is. Number 30, describe and correct the error in finding the vertex of the graph of the function. So negative x plus 8 quantity squared. H is negative 8. The vertex is 0, negative 8. No, that would be the k value that they're trying to concoct right there. It should be negative 8 comma 0. So on number 30, H is inside of the function as an x minus h squared. And although they correctly identified h, they wrote it in the wrong spot. They wrote the vertex in the wrong order. It should be... Okay, should be negative 8 comma 0, right? And you do flip that sign. It has nothing to do with the negative out in front. It just has to do with that. That is h, and it should be negative 8 comma 0, not 0 comma negative 8. Okay, numbers 31 to 34. We are going to find the vertex and axis of symmetry of the graph of the function. It'll be exactly like those other ones that we had before. This should be wicked fast. We are not graphing them, but we are identifying the vertex. This time it's with a plus k involved. So this is going to then be the vertex of negative 4, vertex of negative 4, negative 3, and the axis of symmetry is going to be at x equals negative 4. So the axis of symmetry is not changing just because you vertically translate. Going up or down does not change the axis of symmetry that's up or down to show where heights, points on heights go across. All we're doing is really identifying h and k and just talking about x equals h as the axis. F of x equals, number 32, f of x equals 3 times x minus 3 quantity squared plus 6. Hopefully problems like these do make it go a little bit faster. Vertex is at 3 comma 6, and the axis of symmetry is at x equals 3. Remember, you need the equation. It's not 3. It's definitely not 3 comma 0. It's x equals 3. It's the equation of the line that would make it. Number 33, f of x, and it's x, not y. F of x equals negative 4 times x plus 3 quantity squared plus 1. The vertex is at negative 3, comma, positive 1. And then the axis of symmetry is at x equals negative 3. Okay. And then number 34, y equals negative x minus 6 quantity squared minus 5. I can't really trick you with this unless it's not in vertex form, and these totally are. Negative x minus 6 quantity squared minus 5. I guess sometimes it's good to practice things that you know how to do. The vertex is going to be at 6 comma negative 5, and the axis of symmetry is at x equals 6. Okay, numbers 35 to 38 match the function with its graph. You know, I don't know if I'm going to really write anything besides the letters of the answers here. We could identify vertexes and stuff. I'm going to say those out loud. So, if that's okay with you guys. Really, I want to find the vertexes, whether it faces up or down, things like that, because those could be the only thing that change. So on number 35, we're going to look for a vertex that is, I guess I got to write down the problem. I'm sorry about this. Y equals negative x plus 1 quantity squared minus 3. Yeah, let's do that again. I got to write some stuff down. The vertex, let's see. It goes upside down, and the vertex is at negative 1, negative 3. So is it A, B, C, or D? Even though it goes upside down, it can't be A because that's at 1, 3. But when C goes upside down right there, you can see that's negative 1, negative 3. Number 35 is C, graph C. Number 36, we have y equals negative 1/2 times x minus 1 quantity squared plus 3. Now, I'm not really looking too heavily at the 1/2 portion, just the fact that it's negative, but it would be nice to confirm that this is the graph that they made as well. It should be A as the answer because the vertex, it's upside down, and the vertex is at 1, 3. So that does look like that first one, which will be A. But let's make sure we know how negative 1/2s work. We go over 1 down half of 1, over 2 down half of 4, which is 2, and things like that. Make sure you're still feeling that out. Number 37, we have y equals 1/3 times x minus 1 quantity squared plus 3. See, I wish they had a couple more of these where they had the same they had the same vertex, and the stretch factors were different and state which one's wider, which one's whatever. So x minus 1 squared plus 3, this is right side up facing, and that minimum vertex is at 1, 3. 1, 3. 1, 3, that looks like part D when it faces upward. It also looks vertically compressed. That makes a lot of sense. That's D. And lastly, number 38, we have y equals 2 times x plus 1 quantity squared minus 3. Okay, this is face upward again. Listen, it's process of elimination. It should be, what, B? But the vertex is at negative 1, negative 3, and it's vertically stretched. It seems to kind of work that way. Over 1 up 2, yep, that's going to be B. It's going to be B. And those are all the answers to that one. C, A, D, B. Whoops, let's not move forward there yet. Let's move to number 39. In 39 to 44, graph the function. Compare the graph to the graph of f of x equals x squared. So now we get to graph with h and k in mind. So let's do a couple of these ones. This is really what we want to lead into, I suppose. So h of x, or y, equals x minus 2 quantity squared plus 4. Okay, that vertex is at 2, 4. I'm saying that out loud. Vertex is at 2, 4. If you want to draw the axis of symmetry, I might do it to start with, but otherwise you'll see me later. Just reflect, be my guest. The a value is 1. So I get to go over 1 up 1 squared, over 2 up 2 squared, over 3 up 3 squared, and reflect these points across. It's not symmetric across the y-axis, but it is symmetric across its axis, which is x equals 2. Let's see what else they asked for. Did they ask for domain and range? Let's see. No, compared to the graph of f of x equals x squared. So this one only had translations. We translate the points 2 units up, or right, and 4 units up. Rup. All right, number 40. G of x equals x plus 1 quantity squared minus 7. Okay, so this one The vertex is at -1 comma -7. So all the way down here. And then vertical stretch once again of 1, +1. So it's the same thing. We got 1, 1, 2, 4, 3, 9, 4, 16. No axis this time. 1, 1, 2, 4 at -3. 3, 9 up at 2. 4, 16 up at y equals 9. And can I fit 5, 25? 25 up from, not quite. I don't think even close, actually. Okay. Oh, it is actually really close. It hits at 18 right there. So 25 up from -7 is at 18. I should know that. Okay. It's never straight, no matter what, no matter how we made it. Only translations. We translate. Translate. 1 unit left and 7 units down. All right, start picking up some A values so we can talk some compression. Oh, man, my neck. I can barely turn right. Some stretches, compressions, and reflections. Let's look at number 41. Sorry, I'm going to have a lot of movement now. The way that I have to reach, let's move in a little bit. Number 41, R of x equals 4 times x minus 1 quantity squared minus 5. It will vertically stretch, and we're going to count for that. The -1, -5 is your vertex. Excuse me, 1, -5 is your 1, -5 is your vertex. Over 1 up 4 times 1. Over 2 up 4 times 4. Wait, that's not right. Let me count again. 4, 8. I don't know why I can't count this. Oh, maybe that was right. Okay. Strangely, if I change my position and what I'm trying to do to fix my neck, it hurts another part of my neck, so I'm then doing something wrong. All right. We do translate, but we have to first mention the vertical stretch. We vertically stretch by a factor of 4. And then we translate 1 unit right and 5 units down. Okay. Number 41. All right, number 42, n of x equals -x plus 4 quantity squared plus 2. Okay, so this graph goes upside down because the negative, it is just a -1 though, so there's no stretch or compression with it. It just reflects over the x-axis. So at -4, +2 though is our vertex. And we're going to go downward. 1, 1, 2, 4, 3, 9, 4, 16. And that's all I can fit. And reflect, reflect, reflect. Okay. The graphs go fast if you know what you're doing with them as far as avoiding tables and what we got going. Hopefully that's good. Number 43. G of x equals -1/3 x cubed. Excuse me, it's cubed. That is not our chapter. -1/3 times x plus 3 quantity squared minus 2. Okay, this is the most ambitious one when it comes to the fraction and everything else involved. So the vertex is at -3, -2, over here, over here. -1/3 is we're going to go down, but instead of going down 1, we're going to go down 1/3 of 1. We're going to go down 1/3 of 4 when we go over 2. We go over 3, we'll go down 1/3 of 9, which is 3. Down 1/3 of 16 is 5 1/3. Down 1/3 of 25 is 8 1/3. 6, wait, what did I say? 5 1/3, 6, 7, 8 1/3. And down 36 is 36 thirds, which is 12. Okay. Oh, boy. Hello. Okay. That's an arrow on this side. Let's go ahead and describe it. We got 4 things to describe, sort of. We're going to reflect over the x-axis. We're going to vertically compress by a factor of 1/3. That's A. Then we're going to translate 3 units left and 2 units down. That is H and K. Okay, number 44. Number 44. R of x equals 1/2 times x minus 2 quantity squared minus 4. So the vertex is going to be at 2, negative 4. 2, negative 4. The vertical stretch of 1/2, it's upward because it's positive. Over 1 up half of 1. Over 2 up half of 4. Over 3 up half of 9. Over 4 up half of 16. That's 8. Over 5 up half of 25 and half of 25. That's 12 and a half. Over 6 up half of 36. That's 18. 18 up from negative 4 is 14. I can fit that right here. All right, beautiful looking graph without a table. I hit 1, 2, 3, 4, 5, 6, 7. I hit 13 points on this thing in a matter of seconds. Okay, compare it to f of x equals x squared. There was no reflection, but it compressed. There's a vertical compression by a factor of 1/2. We're going to translate. Again, I believe they say other things like they both open upward. That's what my description of transformations do in comparison, right? They say compare, so apologies to that. The vertex also takes care of things like the min and max value and the domain, and the, not the domain range, the, it kind of does, and the axis of symmetry, sorry. Oh, boy, I hate doing this on video. Okay, numbers 45 to 48, it's another matching bit. So this one's a little bit different, though, because of what they're asking you to, let's see, let f of x equal x minus 2 quantity squared plus 1. So f of x equals x minus 2 quantity squared plus 1. Now let's look at what this graph looks like and compare it to the others so we know exactly what it is we're looking for, if that makes sense. And we can probably mess with that a little bit. X minus 2 quantity squared is plus 1 is at 2, 1. And a vertical stretch factor of 1 will lead me to this graph at 1, 1, 2, 4, 3, 9, and 4, 16. This is the original graph. Now what we're going to do is look at 4 graphs with 4 different equations. They don't show them in their raw form. They show them compared to f of x. And we can maybe look off of that. They don't ask us to graph. They just say to match it. But number 45 has g of x equals f of x minus 1. What we're going to do is translate this thing 1 unit to the right, and then boom, you have your graph. That's it. We move it 1 to the right. So before this was at 2, 1. Now vertex will be at 3, 1 with the exact same graph. I guess all these face upward. So you're going to get but where's 3, 1? Looks like it's this one, A. It's going to be A because it's 3, 1 right there. Now that's the translation 1 unit to the right. If you were confused as far as what actually happens in here, f of x minus 1, what happens is f of x minus 1, being g of x no less, keep in mind that f of x is x minus 2 squared plus 1. F of x minus 1, you take the x minus 1 and substitute it for x. Instead of x minus 2, it'll say x minus 1 minus 2. And that's a substitution. Negative, and this is g of x, by the way, right? Negative 1 minus 2 is negative 3, so this becomes x minus 3 squared plus 1. And you can see that that's why the vertex is where it's supposed to be at 3, 1. if that helps you. Number 46. We have r of x equals f of x plus 2. Once again, it's kind of an x minus h dealio, if you will. The x plus 2 would make this thing go, you have to go 2 to the left to graph it. So where's 2 to the left of here? So 2 left, that's what that means. Just like when it's inside the function. 2 left is at the, not the origin, but at the y-axis at 0, 1. And that's going to be letter C. Letter C. Let her see. Number 47. We have, I didn't skip to 46 on this last thing, I'm sorry. 45, 46. Number 47, we have f of x, or h of x equals f of x plus 2. Notice the plus 2 is on the outside, like a k would be. It affects the y after you plugged in something for x. Therefore, everything's translated 2 units up. 2 up. And that'll be at 3 from the original, and that'll be at 3, 3. So let's find the one at 3, 3. That is, excuse me, 2, 3. 2, 3. B. That is letter B. It looks like D wasn't chosen, so we'll see how D comes into play based off this. Number 48. What color? This is P of x equals f of x minus 3. So once again, it's going to take a translation of what we had before. So, you know, if you were kind of confused, this will go 3 down. But if you're kind of confused on what we're actually doing, we have, again, the original function is f of x equals x minus 2 quantity squared plus 1. Right? Yep. Now, P of x is f of x minus 3, which is taking f of x, boom, and subtracting 3 from it. So that minus 3. Doesn't mean I distribute, nothing like that. I'm going to do 1 minus 3, but I want to bracket what makes f of x, and then we go ahead and subtract 3 from it. We don't plug it in with the x this time. So you can tell what you get here is x minus 2 quantity squared minus 2. That minus 2 is 3 less than if it was from 1. That's why it goes 3 down. That's why it is D. That's why it is D right there. Okay. Numbers 49 to 54, we are going to be graphing G. So I am not going to be graphing F. I'm going to be graphing G, but I'm going to copy down the material. F of x equals 2 times x minus 1 quantity squared plus 1. And then G of x is f of x plus 3. So what we're going to do once again is x plus 3 is going to substitute for x into its equation. Instead of x, it'll say, I'm just going to write it without parentheses, x plus 3 and then minus 1. But that's taking x's place. Instead of x, we have this. But now let's kind of keep simplifying that for ourselves. G of x will be 2 times x plus 2, quantity squared plus 1. They never asked us to graph f. They never asked us to compare to f. They're saying use f's equation, transform g in that way, and then graph the transformation, whether or not f is graphed. So I'm going to go ahead and plot the points for this one here. The vertex is at -2, +1. And the stretch factor of 2 means over 1 up 2, over 2 up 8. If you're still confused on that, you have to go back to the nature of quadratics, what 2 squared is, then times 2. Over 3 up 18, which I can't fit. I wonder if they're going to ask about y-intercepts and some of the word problem things. They tend to kind of explore with you in that kind of way. That is number 49. You just graph it and that's it. Now, I didn't graph the original. But what's the original? It's 3 to the right of that. We go 3 to the left to get this graph here. And that's what that'll be. Number 50. The original f of x is negative, or opposite of x plus 1 quantity squared. Plus 2. We're going to take that. Now this is going to be a little confusing. We're going to take half of f of x. That doesn't mean that we take half of we just replace the negative with 1/2. Nothing like that. No. what we're going to do is take half of f of x. Half of f of x. This whole thing. Which means we distribute the 1/2 into this first term and the second term, just like that. So g of x is going to be negative 1/2 times x plus 1 quantity squared. And then 1/2 of 2 is 1. So you get plus 1 as your equation there. This is what happens when you do a vertical stretch or compression after doing a translation. It affects your translation values. In this case, this plus 1 was a plus 2. If I want to keep it as a plus 2, I describe the vertical translation compressions first, and then I do that. For reasons, right? For reasons. But let's graph this. Negative 1, 1, and down, and we use the halves. Over 1, down half of 1. Over 2, down half of 4. Over 3, down half of 9. Over 4, down half of 16. Over 5, down half of 25. 12.5 from there. And over 6, down half of 36, which is 18, which is right at the bottom. They know my graph too well. Whoops. Okay. Now in old videos, you'll hear me call these 8-second graphs. Was that 8? No. More than a minute, I'm sure. Maybe 8 seconds in comparison to whatever the heck you'd be doing with the table if you had to plot as many points. Number 51. F of x equals negative 3 times x plus 5 quantity squared minus 6. G of x, whoops, equals 2 times f of x. And I really do recommend you do what I'm doing right here next, which is coming up with the equation. Don't just do this part because you'll also have to double the negative 6. You might forget about that. But we are going to remember it right here. We're going to double negative 3 times x plus 5 squared. We're going to double negative 6. So we go ahead and distribute that, and we get negative 6 times x plus 5 quantity squared minus 12. Good luck with me getting enough points for you guys. I'm only going to get 3 in total on this thing. So with this graph, we ignore everything that's up here, and we just go way down here at 0, negative 12, right there. Excuse me, negative 5, negative 12. At negative 5, negative 12. Right there. And then we go over 1 and down 6. Negative 6. So 1 times negative 6 is negative 6. It's already off the graph. As much as I can do, however. And hopefully / simply that should be enough. It's an unfortunate kind of window range thing, but you know, we do what we do with that. That's the answer. Number 52. We have f of x equals 5 times x minus 3 quantity squared minus 1. And g of x equals f of x minus 6. So we're going to translate everything 6 units down. Really what it's going to do is take this negative 1 and make it 6 less. It'll make it negative 7. So g of x is 5 times x minus 3 quantity squared minus 7. Let's go ahead and graph that. Hopefully we can at least get at least one more set of points, I think. Yeah. So 3, negative 7 is our vertex. And we're going to rise and run. Excuse me. We're going to go over 1 up 1 squared times 5. That's 5. And over 2 up 4 times 5. Now 4 times 5 is 20. So up 20 from negative 7 is 13. So I'm on the right x value. I think I am. 1, 2, 1, 2. Okay. There we go. Okay. That's number 52. 2 more on this set. Number 53. F of x equals x plus 3 quantity squared plus 5. We're going to graph. G of x equals f of x minus 4. in order to do that best, we should figure out what g of x actually would be. We're going to substitute x minus 4 in for x. So x minus 4, there's still a plus 3. Squared plus 5. The minus 4 inside this will also mean translate 3 units to the right. So normally we're at negative 3. Now it looks like we're going to be at positive 1. X minus squared plus 5. Positive 1, positive 5 is the vertex for this equation. We're going to go ahead and plot that. Vertical stretch factor of 1. It doesn't stretch at all. So let's check it out. At 1, 5, we're going to go 1, 1, 2, 4, 3, 9, 14. And that's all I can fit. Well, that's good enough for me. That's 53. Let's look at number 54. Last one in this set before we hit some other ones. About 2/3 done now. F of x equals negative 2 times x minus 4 quantity squared minus 8. G of x equals, negative f of x. Okay, so this will, yep. Negative f of x. So what we do is change the sign. G of x equals. Now, not just of this guy, of also this guy right here. The opposite of negative 2 times x, not absolute value. Negative 2 times x minus 4 quantity squared minus 8. That means the negative goes into both parts. So it will be positive 2 times x minus 4 quantity squared and plus 8, not minus 8. We're taking the opposite of all of f of x. This is, if I graphed both together, I guess they wouldn't be a function together, but together they would represent something odd because you're going to see symmetry across the origin there. That some x's get you some y's here, the opposite x's get you opposite y's. Is that right? Is that right when I said that? That might not be true. That, you know what? I take that back. That might not, you know what? That's not true. This didn't change signs right there. So I think I said that wrong. I don't think it's reflecting across the x-axis only. Well, sort of. Then we bring this thing up. It would look cool if I graph both though. So at 4, 8, we're here, and 2 is over 1 up 2, over 2 up 3, 4, 5, 6, 7, 8, right here. At 16. And sketch that. Kind of hope I'm near finished with the graphs. Word problems might have some here and there. And we're dealing with the word problems now. So 55 to, I think, 79, we're going to start dealing with this. They might have some other bits. Modeling with mathematics. The height in meters of a bird diving to catch a fish is represented by h of t equals 5 times t minus 2.5 quantity squared, where t is the number of seconds after beginning the dive. Well, they ask us to graph it to begin with, so that is just my favorite thing to look at. This says the height of the bird diving to catch fish. So what the bird's doing, birds don't just go down or up or whatever, they do both. It's swooping down to catch, and it's coming back up. Now, it doesn't say anything in particular about its angle that it's going at. T is time. This isn't actually the bird's direction. It could be going pretty fast like that. It could be going straight down for all we know. But 2.5 is here, and I'll just work it. This is 2.5 comma 0 over 1 up 1. No, over 1 up 5. I made that mistake one time. Over 1 up 5. Over 2 up 5 times 4 is 20. I can't really fit it. Can I pretend like I can? Maybe something like that. They did ask us to graph it, and that's going to be pretty tall. Okay, sorry about that. So that is part A. Part B. Another bird's dive is represented by r of t equals 2 times h of t. Graph r. So r of t is 2 times h of t, and h of t, so it's going to be 2 times 5 times t minus 2.5 quantity squared. Now notice I only multiply the 2 with the 5. It's not like it distributes to every part. Even if it could, it won't for the case of that's being squared, but that's not how you do it. You only multiply by one part. And 2 times 5 is 10. So 10 times t minus 2.5 comma squared. It's going to swoop down at the same time to catch this fish, only it comes from higher up. It's a lot sharper. I'm going to make it in green right here. So 10, same point, but over 1 up 10. And over 2 up 40. I can't fit that. So I'm going to go ahead and just leave it like this. Nice and skinny. Again, it's not the bird's direction. This is time. But maybe the bird did direct like this. I don't know what they do. What kind of bird is this? Oh, it didn't say. It looks like a pelican? Compare the graphs. Which bid starts its dive from a greater height? Explain. So I kind of just started talking about that. It is going to be R of t. So they said compare the graphs. Same vertex, different vertical stretch factors. Now, which bird started from the greater height? The bird in R of t started at a greater height. They say explain. This is because, let's see, because given the same vertex, it has a higher vertical stretch factor. I mean, we have to make sure that we have to make sure that we understand that what we're saying is at some x we have taller y's. So at x equals 1.5, we have a y here of 5 and a y here of 10. We have taller y's in general. It's at double the height of the other one. That's what the 2 kind of means there. All right, number 56. If they're all parts A, B, and C, I'd be done. Oh, good. That goes maybe a little faster. Parts A, B, and C. A kicker punts a football. The height in yards of the football is represented by that function there, where x is the horizontal distance in yards from the kicker's goal line. They do ask us to graph F. So this one's going to be... I don't know how deep I want to get into this thing. They do ask us to graph some things. Man, they're pushing. They are pushing. Let's see. Because the scale, it's really the scale that's going to be throwing me off so much here. Okay, if I'm going to do that, I'm going to kind of change both of them the same way maybe. Minus 30. So I have so little room to do this thing. If I go by 5s, 5, 10, 13, 20, 25. Can I go by 5s on this other one and still make sense of it? Let's go 25, 50, and negative 25, negative 50. Okay. Graph it. X minus 30 plus 25. So 25, 30, and up at 25 right there. Negative 1/9. Every 5, this is going every 5. So this isn't going to be good. This is going to be kind of hard to say. I'm going over 5. I'm going down. You know what? I can just say I can go 1 and down 1/9 of 1. And 2 down 1/9 of 4. Because it's the same kind of thing. Those scales apply in that kind of way with even these points. At least they should. Over 3 down 1/9 of 9, which is 1. Boy, over 6. Let's just go over 6. Down 1/9 of 36. That's 1, 2, 3, 4. Now I know I'm going by 5s, but that's... I need to hit that point there at least, because that's where they kick it, I think. Now, I don't really hit that bottom one there, but it's going to hit somewhere there as well. On the next possession, the kicker punts the football. The height of the football is represented by g of x equals f of x plus 5. Graph G, describe the domain and range. So, first of all, C graph. Let's do that in black. Next one I'll do in blue. Excuse me, that's part A. Part B, we have this new g of x equals f of x plus 5. This is going to be a translation, 5 units left. Translate 5 left. 5 yards to the left. And so that's going to start right here instead. So it's gonna otherwise be the same graph. They say to graph it. It's going to otherwise be the same graph, but it's going to look like that. Now, is the y-intercept always going to... Wait, hold on. What did they say x was? X is the horizontal distance from the kicker's goal line. Over 6 down. So they kicked it from... X is the distance. They probably kicked it from behind the goal line on this one. Or whatever. I don't know what their heights are that they're doing. I guess you can have negative yardage, basically, is what I'm saying. Describe the domain and range. Yeah, let me... Okay, they said describe. I'm sorry. They said describe. I hope that I didn't tarnish headphone users there. They said describe. Last time I described, I actually found them. So the only question is... Okay, so X. So the domain is the distance... Still the distance from the kicker's goal line. The range... I don't know. It said describe the domain and range of the first one, too. I don't think they want us to actually find the values where they hit certain things, though. What do they want us to describe? They already said what they are. The domain... Oh, I'm sorry. It's not just the distance, because they're saying where it comes from. Okay, let's see. The domain is the distance of the kick. There we go. The range is the height of the ball's path in yards. In yards. Okay. I don't know. The domain is... Kicker punts the football. The height of the football is represented by this. Oh, it's still the height of the football. I thought they were saying that the... Maybe they did. The kicker's just 5 yards farther back. The domain is the height of the distance the football travels. The range is the height of the football. I don't know if I'm doing this right. The height of the football's path, right? Football's path. Okay. Part C, compare the graphs. In which possession does the kicker punt closer to his goal line? Explain. Well, the question is, it says the height of the football is represented by this, where X is the horizontal distance. It depends on where the kicker punts from. See, blue is going to end up hitting down here, which is not closer to the goal line. If that's where they kicked it from. Black, they would kick closer to the goal line. It would be right there. So I imagine they're saying they're kicking it off the ground. That's just my imagination. So when they say compare the graphs, this is translated to 5 to the left. So graph G of X is translated 5 left. That is the comparison. The kicker, I gotta type this. The kicker is closer to the goal line in graph F. The kicker is closer to the goal line with F if we start on the x-axis for the kick. This is because the path crosses the curve. Okay, so there is all of that. Sorry about that. All right, numbers 57 to 62. Write a quadratic function in vertex form whose graph has the given vertex and passes through the given point. I'm going to follow what they do. I'm going to maybe say some out loud if I can tell what it is. I'm going to do this. I'm going to put V for vertex. Vertex is 1, 2, and through the point 3, 10. So I'm going to say what they do here. So we have the equation y equals a times x minus h quantity squared plus k, right? Vertex is h and k. We have an equation that's going to say y equals a times x minus 1 quantity squared plus 2. We need to find out what a is, the a value that would pass through this specific point. So we're going to use this specific point. This was an hk, but we're going to use this xy right here. So y is 10. We can say 10 equals a times 3 minus 1 quantity squared plus 2. 3 minus 1 is 2. 2 squared is 4. So you get 4a plus 2 equals 10. Subtract 2. Divide by 4. You get a equals 2. So your equation will be y equals 2 times x minus 1 quantity squared plus 2. Yes, you bring back the y and the x. We have to make it for the entire graph. We just chose an x and y that worked for that particular instance. Now, here's what I would do. Here's kind of what I look at. It's easier to see it on a graph, but notice how the vertex is at 1, 2. We start at 1. This point, 3. 3 is 2 away. 3 is 2 away from 1. And normally I'd go 2 away. I'd go up 4 for 2 squared. When I say normally, I mean if your stretch factor is 1. But now you're multiplying by some a. 4 times what gives me 8? Where am I getting 8 from? From 2 to 10. The distance from 2 to 10 is 8. 4 times what is 8? 2. So like I said, I might give you some of the answers beforehand if I know what they are, but we're going to go and work this thing out. Vertex is at negative 3, 5, and passes through the point 0, negative 14. Okay, so 0 is 3 away from 3. Normally we'd go up 9, but now we're going to go down, so it's going to be negative, and from 5 to negative 14 is negative 19. We're going to multiply 9 by some number and get negative 19. That's the distance. And then a is going to be negative 19 ninths. That's what I believe I'm going to get as an answer. Let's try it out right now. We have y equals a times x minus h squared plus k. Remember the minus h plus c. 0, negative 14. So negative 14 equals a times 0 plus 3 squared plus 5. 0 plus 3 is 3. 3 squared is 9. We're going to get 9a here. I'm going to subtract 5 from both sides. I can do that right now. That's negative 19. And once again, we're going to get our answer there of a is negative 19 ninths. A very weird number. I'm still doing it mentally over here in the way that I'm kind of coming up with what I would normally go up by and multiply it by a to switch it. And that's what it is. So the equation is going to be y equals negative 19 ninths times x plus 3 quantity squared minus plus 5, I should say. Negative 19 ninths also cannot reduce, by the way. Number 59. Vertex of negative 2, negative 4. And passes through negative 1, negative 6. From negative 2 to negative 1 is 1. And instead of going up 1, we're going down 2. A is going to be negative 2. Let's check it out. Y equals a. Y equals a times x plus 2 quantity squared minus 4. Negative 6 for y. Negative 1 for x. Negative 1 plus 2 is 1. 1 squared is 1 times a is a. Add 4 to both sides. A is going to be negative 2, which is what I got there. And we're going to get y equals now negative 2 times x plus 2 quantity squared minus 4. Now you might be asking, not sure what I want to say. You might be asking Mr. Robinson how you do that so fast. I forget exactly what I was going to say, but it's just knowing the concepts of these things here, right? It's just knowing the concepts of these things. It's showing that you can get there as well. Number 60. Vertex is 1, 8. Passes through 3, 12. From 1 to 3 is 2. 2 squared is 4. 4 times what gives me 4? Looks like 1. We go from 8 to 12 when we go over 2. So your a should be 1. Oh, I know what I was going to say. I'm sorry. It had nothing to do with me graphing and stuff. You might say, Mr. Robinson, why are you writing this equation first when you're going to substitute these into here? Why don't you do it at the same time as these? One, you don't want to get lost in what's HK versus what's XY. Number two, you want to remind yourself of what's missing from here. And number three, you want to tell yourself where you're at this point and say, here's what I'm trying to get. I have everything but what I'm missing in terms of A. And then we plug in the XY from there. So that's what I'm going to do here. Same thing. Y equals A times X minus H squared plus K, like that. Now I substitute 3 for X and 12 for Y to find out the A value from this specific set, because it should give you the same A value no matter what. 3 minus 1 is 2. 2 squared is 4. I got 4A equals 12 minus 8 over here is 4. Divide both sides by 4. I get A equals 1, just like I said over there. And this is going to be Y equals 1, or just nothing, times X minus 1 squared plus 8. And I don't mean literally nothing. I don't mean a 0. I mean nothing visible. Two more, number 61. 61. Not f of x. Vertex is at 5, negative 2. You're going to pass through the point P of 7, 0. From 5 to 7 is 2. 2 squared is 4. Normally I'd go up 4, but we're going up half of that from negative 2 to 0. Your A is going to be 1/2. All right, let's check it out. Y equals A times X minus 5 quantity squared minus 2. We're going to substitute 7 for X, 0 for Y. 0 is A times 7 minus 5 squared minus 2. I'm going to add 2 to both sides right now. The 0 is lonely. 2 equals A times 2 squared, 4A. Divide both sides by 4, and you get A of 1/2. You're saying, Mr. Robinson, can you just do your way? Can we? Well, you can fast forward through this. This is for anybody else, but I will keep doing my way. 1/2 times X minus 5 quantity squared minus 2. Okay, and lastly on this set, number 62, we have vertex of negative 5, negative 1 passing through negative 2, 2. Vertex of all right, we're going from negative 5 to negative 2. That is 3, a run 3. Instead of going up 9, we're going up 3. Going up 3 is 1/3 of 9. If 9 times A is 3, then A is 1/3. That's what we're going to get there. Let's see if we can get to that. Y equals A times X minus H quantity squared plus K. And again, I'm saying them out loud based on how you do minus a negative. Let's substitute negative 2 for X and 2 for Y. 2 is A times negative 2 plus 5 squared minus 1. That's 3 squared. And 3 squared is 9. If I add 1 over, I get 3. And you can see we get to the same concept as before. 3 is 9A. Divide both sides by 9. You get 1/3. So your final answer is going to be Y equals 1/3 times X plus 5 quantity squared minus 1. There's more that we can talk about with that thing as far as what I'm doing and why it actually fits and works. I think the idea is you got to really understand the concept of your graphs. But more so in your equation, you can see I didn't square 5, or what was it, negative 2. I squared 3 because my distance from my vertex, all that kind of stuff. Okay, let's see what we got going next. Modeling with mathematics, a portion of a roller coaster track is in the shape of a parabola. Write and graph a quadratic function that models this portion of the roller coaster with a maximum height of 90 feet, represented by the vertex 25, 90, passing to the point 50, 0. I think it's more of the same here, just when it comes to vertex. Y equals A times X minus H. That's a 25. The 25 is a part, it's not time, I think it's just how many feet over. 25 feet over, you're 90 feet up from whatever they're referring to. By the way, don't forget your squares. A lot of people forget this thing right here. We are talking about quadratics, right? So this thing's squared here. So we're going to be passing through 50, 0. Okay, we're going to get, 0. 0 equals, what are we going from? 25, 90 to 50, 0. When I go 25 over, instead of going 625 up, I'm going 90 down. So whatever negative 90 divided by 625 is, that's what we're going to be doing as well. So 0 equals A times X is 50. 50 minus 25 squared plus 90. I'm going to subtract 90 over. And I'm going to do A times 25 squared. 25 squared is 625. And that's what I was saying before. Your A value is going to be negative 90 over 625. Now, at the very least, I can divide it by 5. And that might be it. Because then I'll get negative 18 over positive 125. Wait. Yeah. And 125 can't divide by 3 like 18 can or anything like that. That would be it for that. The equation that I can now say, write and graph, they said graph it. Y equals negative 18 over 125 times x minus 25 quantity squared plus 90. Okay, as far as graphing, I'm not going to graph to scale. Not at all. No. What's interesting as a question is, I don't know if I could answer it from this, is, I guess, okay, this I'll have to do later, I get it with factored form, but axis of symmetry I think also works. 25 here, 90 here, and they said 50 comma 0. So if I have 50 comma 0, yeah, this will still work, and it's 25 away from 25, then on the other side would be the other vertex right there. So when it comes to graphing, not vertex, the other y-intercept, the other corresponding point. So these guys would do that right there. There's the concept of that graph. They said this portion of the roller coaster, I'm going to assume it goes down lower or something like that. Maybe it can hit tunnels. Otherwise, I don't really know. But there's that graph. Oh boy. Hopefully I'm kind of almost done. Got about 15 questions left. 64. A flare is launched from a boat and travels in a parabolic path until reaching the water. Write and graph a quadratic. Another graph. 64. Write and graph a quadratic function that models the path of the flare with a maximum height of 300 meters landing by. Okay, so kind of all the same stuff as before. What did I start? Okay, we have to come up with the equation. So we have a vertex of 59 comma 300, and we have a point when it lands in water at 119 comma 0. From 59 to 119 is 60. So we go over 60. Normally we'd go up 3,600, but now we're going down 300. So it'll be negative, I guess negative 112. We'll see if I get A of negative 112. Negative 112, I think those are numbers. So let's see. My HK, I got Y equals A times X minus 59 quantity squared plus 300. 0 for Y, and then solving for A, 119 for X, 119 minus 59, squared plus 300. Let's subtract 300 over. I get negative 300 equals A times 60 squared. And 60 squared is 3,600. Negative 300 equals A, 3,600, 3,600 times A. Divide by 3,600, A is negative 300 over 3,600. 300 over 3,600 is negative 3 over 36, and that reduces to negative 1/12. Yes. Impressed? Your Y is negative 1/12. X minus 59. X minus 59 squared plus 300. Okay, they asked us to graph this, and it hits 119 comma 0, which is just out of reach of being exactly the halfway mark on this graph here. So I'm going to make a graph that does the same kind of bits, where 59 comma 300, 59 and 300, 300 is the maximum height, and go ahead and hit it way up there. Now, it hits 119 comma 0. 119 is just more than double 59. That's when it hits the water. So on this side, because that's 60 away, right? 60 away from 59 is negative 1 right there. And that's where that guy hits that. How come? Because a flare is launched from a boat and travels about. Excuse me. It might be shooting off right here. Now, I don't know the actual value, but it might be a tick in the air when you're doing it. Just a tick in the air when you're doing it. There's the graph. Okay, numbers 65 to 68. Rewrite the quadratic equation in vertex form. Now, you haven't yet learned what's known as completing the square. But what we can do is come up with the vertex and plug it into vertex form. What I do want to make mention of is this. This is standard form. This is vertex form. They all have their uses. I like vertex form a lot more for graphing. I like standard form a lot more for a lot of other things. But notice this A is the same. It's a vertical stretch factor. You're going to get that A out of there, or you're going to use the A with some of the things that you do. So how do we get into vertex form? We got to find the vertex. How do you find the vertex? The x value is at negative b over 2a. This is 8 over 4, which is 2. The y value for this, we're going to do 2 times 2 squared minus 8 times 2 plus 4. 2 squared is 4 times 2 is 8. Minus 16 is negative 8. Plus 4 is negative 4. So your vertex is at 2, negative 4. The a value is 2. So we know h, k, and a. That's the important part. We know h, k, and a. So this is going to be y equals 2 times x minus 2 quantity squared minus 4. That is the vertex form equivalent of that. You can use negative b over 2a to find it and then insert them into the equation. They do represent your h and k. Number 66. Y equals 3x squared plus 6x minus 1. Let's go ahead and find the x value, the vertex first, given that a is going to be 3, right? So the x value is negative b is negative 6 over 2a. That's negative 6 over 6, which is negative 1. The y value, we're going to do 3 times negative 1 squared plus 6 times negative 1 minus 1. So that's going to be negative 1 squared is 1 times 3 is 3. Minus 6 is negative 3. Minus 1 is negative 4. So we are getting an x of negative 1, a y of negative 4 for the vertex. And your a value, of course, was 3. So this equation is going to say y equals, instead, 3 times x plus 1 quantity squared minus 4. Keep in mind what we do there. Did I do that for a second time? I want to kind of circle that afterward. Okay, that is number 66. Number 67. F of x equals negative 5. How long have I gone? Hour 52, almost 2 hours. F of x equals negative 5x squared plus 10x plus 3. The vertex x value is going to be at negative b over 2a. Whew. I'm trouble writing. Which is negative 10 over negative 10, which is positive 1. The y value is negative 5 times 1 squared plus 10 times 1 plus 3. That's negative 5 plus 10, which is 5, plus 3, which is 8. So your vertex here is at 1, 8. Your a value is negative 5. That doesn't change. So your equation is y equals negative 5 times x minus 1 quantity squared plus 8. And lastly, on this set, number 68, we have f of x equals negative x squared minus 4x minus 2. I prefer completing the square on all of these problems, but you haven't learned it yet, not until chapter 4. Even then, you probably won't prefer it. I'll say that much. The vertex, the x value is negative b over 2a. The a is negative 1. Opposite of negative 4 is positive 4, but hey, we divide by negative 2. Therefore, we get a negative 2 for x. And then the y value, by substituting negative 2 into here, we're going to do the opposite of negative 2 squared minus 4 times negative 2 plus 2. Negative 2 squared is 4. Opposite of that is negative 4. We're going to do plus 8, which is positive 4, plus 2 is positive 6. So your vertex is at negative 2, 6, and your a value is negative 1. So this is going to be the equation y equals negative 1, or negative x plus 2 quantity squared plus 6. The plus 2 or minus negative 2. That is number 68. Okay, number 69, can a function be symmetric about the x-axis? Explain. So, yeah, you know, it's an interesting point when we ask the question, why do even functions go symmetric across y and odd functions go symmetric across the origin? Why don't they go symmetric across the x-axis? Well, those are just names. I mean, they do have to do with odd degrees and stuff. That does help. But how about an even function? Excuse me, how about a function that would somehow have symmetry, say like that? Like, boom. There's symmetry across the x-axis. I flip it over and I get the same point here as I do there for different y's. I get the same x. It's not a function. It's not a function. It fails the vertical line test. Fails vertical line test. 2 y's for the same x. You can't have that. Can a function be symmetric across the x-axis? No. It's no longer a function. Can a relation? Yeah. Like circles and stuff, they exist. Sideways parabolas. How do you see it? The graph of a quadratic function is shown. Determine which symbols to use to complete the vertex form of the quadratic equation. Explain your reasoning. So the a says whatever. It's going to be whatever a value. It seems like that, right? We're only using it to complete this thing. So, okay. X in 2 squared and then with a 3. The 3, this is at negative 2 comma 3 for the vertex. This is plus 2 minus 3. They ask you to explain. No. The vertex is at HK. I'll just say this. The vertex is at HK. And the formula is y equals a times x minus h squared plus k. Whoops. Plus k. So the minus h part is that we will be, let's see, h is negative 2 and k is negative 3. So subtracting the negative obviously turns the h into that kind of thing right there. So that'd be that. They just use the a. They just say it's a. We could have found out what it was. A would have been 1. Yeah, I don't know why they put an a there specifically. All right, 10 more problems. No, 9 more problems. In exercises 71 to 74, describe the transformation from the graph of f to the graph of h. Write an equation of h in terms of x. Now, I did some of this before. F of x is negative x plus 1 quantity squared minus 2. H of x is f of x plus 4. Now, before I did it in terms of x myself, just to graph them, so I'm going to do the same thing here. Describing the transformations, f of x plus 4, we're going to say then instead it's f of x, it's this guy, plus 4. Now, I'm not changing color, but here's my f of x, and then the plus 4. Negative 2 plus 4 is what combines, and this becomes negative x plus 1 quantity squared plus 2. That's the in terms of x part. Describing the transformation, that plus 4 is you translate 4 units up. That's like a k just for the function itself. This actual k is 2. The other k was negative 2. That's 4 units higher. And that's the only thing that changes there. So describing the transformation, there it is. Writing the equation in terms of x, there it is. Number 72. We have f of x equals 2 times x minus 1 quantity squared plus 1. We have h of x equals f of x minus 5. Now this x minus 5, it's kind of like the same thing as the x minus 1. I mean, we're going to put something in there, but it's like the same thing. This is at 1 comma 1, you know, it's 1 unit to the right. This is 5 units to the right. So we're going to translate 5 units right. And if you don't believe me, we'll see what the new vertex is here. But of course, we've done some questions like it where we already did this. So it's nice that we have that. Are we graphing them? No. Okay. So we're going to do h of x equals f of x minus 5. X minus 5 is going to take x's place in the equation of f. Instead of x, it'll say x minus 5, and that's minus 1. And negative 5 minus 1 is negative 6. So x minus 6 squared plus 1. So note, the vertex of the original one would have been at 1 comma 1. This one's at 6 comma 1. Where is 6 comma 1? 5 units to the right of 1 comma 1. And that's the translation of that. 2 more of those. Number 73, we get f of x equals 4 times the quantity x minus 2 squared plus 3. And h of x is 2 times f of x. Now, I mentioned this one before. I have to make sure I describe the transformation properly for you, that it makes sense. But this h of x here, we're doubling all that is f of x. We're doubling not just 4. It's not just going from 4 to there. Everything gets doubled. That means also the 3. Also the 3. So that's going to become 8. Yes, but that translation is also plus 6. We're going to vertically stretch. We're vertically stretching f of x. By a factor of 2. We're taking the y values that they had as well, and we are stretching them twice as tall, starting from the vertex, and kind of every point after that, that instead of 1, 1, it's 1, 2, instead of 2, 4, it's 2, 8, things like that. So everything gets stretched vertically. Number 74 looks like a horizontal compression, but let's see where we go with it. F of x equals negative x plus 5 quantity squared minus 6. And h of x is 1/3 of f of x. Give me 1 second. Okay, am I back? Yes, I'm back. Okay, so 1/3 of f of x. So now we're going to go ahead and take 1/3 of that whole thing. 1/3 of negative x plus 5 quantity squared minus 6. Distribute the 1/3 into the negative 1 and into the negative 6 here as the different terms. We're going to have h of x equals negative 1/3 times x plus 5 quantity squared minus 2. 1/3 of 6 is 2, and that's what we get there. Now, I've kind of mentioned before, you may be wondering, why aren't you distributing it into here? 1, it's protected by the squared part. 2, we already integrated it into the front of the product. I mean, 3, when you think of it logically, the 1/3 is just a vertical compression. Vertical, it doesn't affect anything on the inside horizontally. I mean, that's just more on the logic basis. But this one's a vertical compression. We vertically compress f by a factor of 1/3 f. By a factor of 1/3. Okay. Let's go to number 75. The graph of y equals x squared is translated 2 units right and 5 units down. Well, I know what I want for my... Not for my vertex, though. Oh, yeah, I want for my vertex. Write an equation for the function in vertex form and in standard form. Describe advantages of writing the function in each form. Okay, so there are parts after that. So we have y equals x squared. We want to translate 2 units right and 5 down. Okay, so one version, listen, I'm going to make up my own with a different a value. I'm going to say y equals, let's use 4. 4, I think I did that before, times x minus 2 quantity squared minus 5. And hopefully you're pretty good on that little bit right there. Now they asked, this is vertex form. They said write it in vertex form and standard form, and this is vertex form. Now to get into standard form, I need to take this equation and I need to expand it. So in terms of expanding it, let's first take care of the x minus 2 quantity squared. 4 can't distribute into that until I square it anyway. So I get x squared minus 4x plus 4. That's how you expand that. It's not just x squared minus 2 squared. 4 distributes into this now. And again, it's kind of open-ended since I put a 4 there, right? If you didn't put a number there, you just have this part. But now this becomes 4x squared minus 16x plus 16, and then minus 5. So this becomes 4x squared minus 16x plus 11. And this is the standard form equivalent of this guy. This is standard form. So vertex form here, standard form here. Now I'm not going to say I can only get standard form from this. This is the only way I'd personally be getting it for myself, though. That's the standard form bit. Notice the reason I wanted to bring out the 4 was 2 reasons. 1, because I want to talk about how you expand first this way before you multiply by 4. 2, I want to show you that you get the same a value from here. They both have their different things. They said describe advantages of writing the function in each form. Vertex form, not of getting it into that, but of writing. Well, I guess that's what they mean. So vertex form advantages reveals stretch factor and vertex and can immediately get into it from translations. The standard form equation, however, on the other hand, standard form advantages, it reveals the stretch factor and the y-intercept. If you recall, the y-intercept is the c value at 11, I guess in this case right here. And that's kind of it. You have to get in this form after expanding this thing out, at least from what I had, or that's going to be one of the easier ways to do that, and that is what that is. That's it, and that's all. All right, 76, 4 more problems. Thought-provoking. Which of the following are true? Justify your answers. Okay, let's take a look at these. A. Any constant multiple of an even function is even. Any constant multiple of an even function is even. True. True. So what they're saying is if I take an even function and I multiply it by a number, if I multiply an even function by 2 or by -5 or by 0 or by 0.7 or whatever, it still stays an even function. The polynomials stay. Sorry, the terms, I'm not really sure how to say this, but just true. Only affected, really, by degrees. Only affected by change in degree. How about that? Which this does not do. Okay, which this does not do. I'm not going to write that. B. I'm going to type these, actually. My hand is really cranking up, and I have a lot to write. My pen is really getting messed up there. So 76 A was true. Only gets changed if there is a change in degree. Which this will not do. Okay, B. Any constant multiple of an odd function is odd. Mostly true, but it's false for at least one of them. False if the constant multiple is 0, then the function becomes even. See, when you multiply something by 0, 0 is a constant value. 0 is an even degree. It's to the 0 power. It's an even degree term. So that would make it even. Anything else should be fine, I think. It says any constant multiple. C, the sum or difference of two even functions is even. Should also still be true. Degrees still don't change. The sum or difference of two odd functions is odd. That could be false, because if terms cancel, you could be left with 0, which would be an even function. So I think if everything cancels there. E, the sum or difference of an even function and an odd function is odd. That is false. That's going to be a neither. That is a neither case. If you have a combination of evens and odds, that is a neither. Hopefully I answered that correctly. It's all about the B and D turning into 0, which makes that thing even, technically. 77, comparing functions. A cross-section of a bird bath can be modeled by y equals 1 over 81 times that x minus 18 quantity squared minus 4. Okay? Y equals 1 over 81 times x minus 18 quantity squared minus 4. Where x and y are measured in inches, the graph shows the cross-section of another bird bath, where we have y equals 2/75 times, x squared, hold on. X squared minus 4/5 x. Now this one is kind of standard form. This has a plus 0 right there, but this one's standard form. This one's vertex form. Which bird bath is deeper? Explain. Which bird bath is wider? Explain. Okay, as far as those go, the deeper one, you're going to have to figure out what the vertex of both of them are. So for part A, the vertex of this guy is going to be at 18 comma negative 4. That's the vertex here. This vertex, because it's in standard form, we have to go ahead and get that. So the vertex x value is negative b over 2a, which is 4/5 divided by 4/75. The 4's kind of cancel. You're left with 1's there, and you're left with 75 over 5. I'm just going to have to go kind of fast on this. 75 over 5, which is 15. The x value is 15. The y value is 2/75 times 15 squared minus 4/5 times 15 and plus 0. I'm just going to leave that. 15 squared is 225. 75 divided by that is 3 times 2 is 6. So I get 6 here minus 4/5 of 15 is 12. That's negative 12. Or negative 6, I should say. Negative 6. So this vertex is going to be at 15 comma negative 6. Now they asked which one is deeper. The deeper one is the one with the smaller y value here, the negative 6. The second birdbath is deeper. The second birdbath is deeper. The vertex reveals a lower minimum. The vertex reveals a 2-inch lower minimum. Okay, that's part A. Part B, which birdbath is wider? Explain. Now, the second one, or the first, excuse me, the one on the, I didn't even notice that they had, so notice on this one here, they even kind of show how deep it'll go, kind of like there-ish. It goes -2, -4, -6. Yeah, I could have gotten it right there. But I think they wanted us to use some of this stuff. I'm not sure. I didn't actually look at this. Maybe I should actually just looked at this graph. I guess it's at -16 right there. Okay, fine. Let's look at it for this next one, but we can use the numbers. Which one's wider? This one has a vertex at 18, -4. That 18 means it kind of goes, they kind of have that same birdbath-ish kind of thing, but it hits 18 right there. Oh, and -4 though, right? So 18 kind of like there, and then it goes back up there to complete it. So it goes wider out. It's going to go 36 inches out. So the first birdbath is wider. Now this is because of the vertex being the halfway mark, right? They're symmetrical. The vertex shows a wider halfway point. And that's all that matters. If it's wider halfway, then it's wider the full way because they're symmetric in that way. All right, 2 more questions. Number 78. Compare the graphs of y equals 2x squared plus 8x plus 8 and y equals x squared without graphing the functions. How can factoring help you compare the parabolas? Explain. So on number 78, we have y equals 2x squared plus 8x plus 8. I'm not allowed to graph it. I'm just allowed to talk about it. Compare the graphs. I'll factor eventually. They first asked me to kind of do some other stuff. I'm going to start with the vertex here. And this would give me an x value of -b over 2a, which is -8 over 4, which is -2. The y value is 2 times -2 squared plus 8 times -2 plus 8, which is 2 squared root of 4, 8, minus 16 is -8 plus 8 is 0. So we have a vertex of -2 comma 0, which is interesting. So there's that. So another form of this is y equals 2, that's still the a value, times x plus 2 quantity squared. Whereas the other graph, the initial, is y equals 1 times x minus 0 quantity squared. So, y equals x squared. So we can kind of compare these two here. So we'll start with, compare the graphs. The second, or the, it is, I'll say it is vertically stretched by a factor of 2 and is translated 2 units to the left. Remember, the -2. That's a -2 or +2 there. Translated 2 units left. They said about the factoring, though. How can factoring help you compare the parabolas? Well, I don't know if they really actually wanted me to do that first, but now that I see what it becomes, I can factor a 2 out of here, and I get x squared plus 4x plus 4. And I notice, hey, I have a perfect square trinomial. And that factors down to x plus 2 quantity squared. I think that's helpful right there. It kind of helps reveals that this was a perfect square trinomial. So given that the factorization led to a perfect square trinomial, it also brings me to vertex form immediately. So that's really cool. Kind of gets me right into vertex form. I can use that based on what I'm talking about there, and that's good. I like it. All right, last question. Your friend says all absolute value functions are even because there's symmetry. Is your friend correct? Explain. So what your friend is referring to is the concept of even functions to begin with, and absolute value functions kind of having that notion. So an absolute value function can say go here, and boom, it's even because it's symmetric across, the y-axis. But I can dispute this to my friend because I can say that, hey, what if it's right there? It's no longer even. Once it's horizontally shifted, it is no longer even. So your friend, sometimes the dum-dum, your friend is incorrect because a horizontal shift off of the y-axis of your absolute value function would no longer make it symmetrical across the y-axis. And that's important because, you'd have a new axis of symmetry. Your axis of symmetry would translate with it, alongside it, with it. I don't know. So yeah, if the axis of symmetry is not the y-axis, then it's not symmetrical across the y-axis. And if it's not symmetrical across the y-axis, then it's not even. They are even to begin with, though. So it begins even, whether it's here, 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 taller, shorter, flipped over, that kind of thing. Even if I just did flip that over, it would still be symmetric across the y-axis. But once I move it, boom. Once I move it, boom, whatever. It's no longer symmetrical across the y-axis. All right, guys, and that ought to do it for this one. Yet another very long video where I'm just, oh, man, I'm in a daze. My eyes got really red from that one. So that ought to do it, guys. This is Mr. Robinson. Thank you so much for watching. I believe the next one starts talking about factored form in general. So we just hit a couple of, that last problem, we did do something about factoring and mentioning it. So we're going to do more on graphing factored form then. I'll see you later. Take care.